solving multiple mode shapes using eigenvalues. So I have a picture of a plane, which I want to pull in. I'll just draw it because I want to talk through how we should make this, right? So let's pretend you got a plane. In the notes, I went through the effort to get you a picture of a Beechcraft Baron. That's my... Ooh, man, if Wichita could see me now. Be like, what have you done to our... That's not so bad. That's right. I'm in the aerospace department. Okay. Beechcraft Barons have two engines, two opposed Continental 0600s, and those are propellers, if you're wondering what those things are. So let's get our mode shapes for our wings, right? If we want to describe this plane and we want to get the first, couple of mode shapes, so 3 mode shapes, we could say take a cross section of our wing. That maybe looks like this, right? We have a mass, and we have a smaller mass, and a smaller mass, right? So this is an engine, a fuselage. How do you spell fuselage? F-U-E-L-S-O-L-G-E. God. It holds fuel, right? And then our other engine. Did that make sense? Okay, so before we go any further, what's the first 3 mode shapes? If we had a board, I'd ask you to come write it on the board. What's the first mode shape?
U.
All right, Jude says a U. Who agrees with Jude? The first mode shape is a U. 1. All right. What do you think the first mode shape is?
No, I think it is a U.
All right, 2. What do you think the first mode shape is? Yeah, but what do you think? I don't know a lot of things. I have opinions on everything. All right, against the U. First mode shape? Going against the grain. First mode shape? You got you, them all going together, or make one up. Come on, Igor. So kind of that sounds like a U, right? Like up in the edges and down in the middle, maybe. All right. What?
That, and it comes down, and it comes like that.
So you have 3 masses. Are you drawing something that looks like that? I mean, do these masses go up and down? So
They go together.
they go to. Oh, you think they all move up together? Is that what you're saying? So
I'll say the middle one stays, and then the other ones move together.
Yeah. So Jude called it a U. I'm going to call it a V. That work? I assume that's what you all meant by U. Yeah. Yeah. Okay. Those are all good answers. We'll solve through. It's a free body, right? So you kind of have to think about what your first mode of a free body is, which isn't something that we've done in this class yet, which is why we're doing this example. All right. Now we need to build a 3-mass system. How do we draw our mass system? Can we just use this? Let's call this M, maybe like 4M and M. Right? Because we're more used to things that look like this, right? Right? and maybe a spring. Okay, but we can also, remember when we had a cantilever beam, right? And we converted a cantilever beam to something that looked like a point mass to this. Remember when we did that? Well, maybe we should just do that here, right? Let's try that. So let's just put 3 of those in. That's an M if you can't figure it out.
So wouldn't the middle one be 4M?
Fine, that's 4M. I don't care.
I'm sticking here.
All right. Oh, what about that? You think that'll work?
Is the bottom a slider or like a fixity?
Yeah, it should probably be a fixity. I think I drew it as a slider. I meant to draw a fixity. I was up all night making mistakes on Word documents. Okay. Does that work? Yeah. Right? I mean, that's not really a representation of this at all, is it? Because here we're connected to the mass, and here we're connected to ground. There's actually no ground on this one. So this is probably pretty wrong, right? Should we just go with that's wrong? Oh, you like it?
All models are wrong.
Well, is it useful?
I'd say so.
How is it useful?
If we connect the 3 masses.
Well, now this is getting confusing. How do you want to connect the 3 masses?
That's where I stop at.
All right. Anyone have a guess on where they want to connect the 3 masses? But this is 3 independent systems, right? And what do we have here? 1 system. So these are not the same. One of these things is not like the other. Right? How should we connect these then? Anyone have a shot?
Yeah, just draw a horizontal.
Let's do that. So we draw a horizontal spring. Maybe something like that. What about these grounds? Are we fixed to any ground? Let's see if the pen lets do that. What? No.
Can you fix it or is it?
But does it need to be fixed? Is this fixed?
No.
No. So let's just get rid of these. Right? Okay, so before I guess we didn't label it, but which way on this plane model, on the stick mass model, what's the degrees of freedom that we wanna that we're interested in?
1, 2, and maybe 3.
Yeah, like what way are they gonna act? Up and down? That would be a good one. So let's just go like 1, 2, and 3, right? Okay, so what about heat? So that makes sense, right? So we're going to get the 3 modes. We're going to get the first 3 modes in our vertical displacement. So we're going to ignore any modes that are like the wings moving forward and backwards, any modes that are torsional. We don't have those degrees of freedom. But what about what?
But wouldn't in this model, like, this model makes me think that the motors are going in and out closer to the fuselage, further away.
What model?
Like the mass spring model.
Yeah, which way should your degrees of freedom be then?
Up and down.
Okay, so you want them like 1, 2, 3? Okay. Kind of rough on your springs.
Yeah, that's what I'm wondering, because if it was, the masses were to move like that, I would think that the fuselage is getting like further away and closer to the motor. Not quite right.
Or maybe, I mean, but maybe it should be like this. M1, I'm just going to call it M, I don't care. 2, M3. right? Maybe it should be like that. Or what if we drew this like this? Anybody here have an artistic side? Because if you do, this is going to annoy you. Oh, that's my spring. How about that? Right? So I've got a fixity here, and then my springs are moving with relative fixity.
Would it be kind of a base excitation problem?
Yeah, yeah, kinda. But let's take a step back. So, okay, so first, it could be a base excitation. So this could quickly diverge into something very complicated, right? But let's take a step back. When we solve for eigenvalues, what does our eigenvalue problem know about? So it knows, so let's take like a generalized eigenvalue problem, right? What is it, like M, let's not butcher this. KV equals lambda MV, right? Maybe something like that. So what does this know about the system? It knows about the transformation from one matrix to another, right? So our model here doesn't have to be easily relatable to this. It has to be mathematically correct, right? So if we build our stiffness of these springs as a function of the stiffness of the cantilever beam, right? So that's K equals 3EI over L. Does everyone agree with that? Remember where that came from? As long as the information about the shape is encoded in this K, we can just use this model. Does that make sense? Right? Because this one, to my mind, looks better, right? Because it's closer to the airplane. But mathematically, this one is also correct, right? So you could start to think, oh, but now you're solving for, so like Jude said, aren't you solving for the mode shapes of the motors going in and out? Are you solving for that? Yeah, because we use the K value that correctly accounts for it. And I just realized that I printed off the wrong notes, but that's fine. Make sure. Right, so I've got a nice figure then. Maybe I don't have a nice figure. That looks like this. So the fact this K value, right, this gives us K, which then gives us this value. But that's what allows us to solve for our mode shapes up and down. Does that sound all right? So should we go ahead and solve for our mode shapes then? Let me make sure I have what I want here. Okay, good. So let's go ahead and solve for our mode shapes. Okay, so we can go ahead and model this as we're going to have a system. I guess it was 2M, but whatever. So mass matrix, our mass times 1, 0, 0, 0, 2, 0, 0, 0, 1. Right? We just make that 2. So that's our mass values. Do we have any damping? Oh wait, sorry. We need our vector. I'm lazy. I'm gonna just write x double dot vector plus. We have any damping? No. So we're just gonna drop that. Now we need our stiffness. So our stiffness, we're gonna pull that 3 EI over L out. That's a constant. And we're going to have 3, negative 3, 0, negative 3, 6, negative 3, or whatever that was, 0, negative 3, 3. X vector is equal to a 0 vector, right? No input forcing. We're just going for our natural degrees of freedom here. Okay, anyone have any questions on how we got that? Yeah, right. So, well, this whole bit here is your M matrix, and this whole bit here is your K matrix. But I pulled out the constants because we just don't apply them, and it helps with the eigenvalue solutions. If you had values, you could put them in, you would get the same answers. It's just everything normalizes out in your mode shapes. Does that make sense? All right, so remember there was 2 different ways we could solve for this. 2 different eigenvalue approaches. We talked about it briefly. Anyone remember the 2 approaches? We have a generalized eigenvalue approach where we have K and M in our eigenvalue problem. Or we can use a mass normalized approach, right? And the difference is when we have our mode shapes at the end, if we use a mass normalized approach, we have to multiply by the M inverse matrix, or M inverse square root matrix. So let's start with the mass normalized approach. Mass normalized stiffness matrix. And what do we call that? K, what's on top of the K? Tilde, yeah. Right? So the first step here is to get m to the negative 1/2, which is equal to 1 over the square root of m um, 1 to the negative 1/2 is 1. 0.51, and then a bunch of other zeros. That's a 0, not a 6. That sound good? Anyone have an issue so far? Okay, so K tilde. I have no idea. K tilde is equal to m to the negative 1/2 K m to the negative 1/2, which is equal to 3 EI over L. 3 negative 1.5, 0, negative 1.5, 1.5, negative 1.5, 0, negative 1.5, 3. Right. Obviously, I've pre-solved these. I am not doing them in my head. So, but anyone have any questions about that? That makes sense. Just basic pointwise linear algebra. Okay, how do we set up our eigenvalue problem then? What's the formulation for the eigenvalue problem here? What's a single matrix eigenvalue problem. How's that written? If you Wikipedia it, what do you see? Somebody want to Wikipedia it real quick? What's that? What's a single matrix eigenvalue problem look like? Or how do we set this one up? So it's A, your matrix vector equals values vector, right? And so instead of A, what do we use here? K tilde, right? So it's K tilde vector equal lambda vector. And you can solve that by putting the determinant of that equal to 0 and finding your roots and then getting your lambda values and then multiplying your lambda values through to get your vectors. Or you can put it into MATLAB, right? Or Python. I use Python. So how many eigenvalues are you going to get here? 3, right? So your first 3 mode shapes now. So this is more mode shapes than we've ever solved for before. What a revolutionary. All right. What's your first? So my first mode shape is, my first eigenvalue, these are not frequencies, is 0. Eigenvalue of 2 is equal to 3. And eigenvalue of 3 is equal to 4.5. I also get eigenvectors. V1 that needs to be corrected. That needs an arrow. So V1 is equal to 0.40 or 41, but whatever. 0.82, 0.41. I'll go 41. I'm truncating a lot, but that's fine. V2 vector is equal to negative 7.070, negative 7.07. V vector 3 is equal, I would suggest you write these down because there is a point to this, I promise. 0.57, negative 0.57, 0.57. You'll learn more when you take notes. Okay. Our first eigenvalue is 0. What does that mean? Or maybe we should solve for our maybe we should just solve for our lambda 1 before we talk too much, right? So lambda 1 is equal to the square root. Sorry, omega 1 is equal to the square root of lambda 1, which is equal to 0 radians per second. Omega 2 equal to the square root of 3, which is 1.73 radians per second. And omega 3 is equal to 2.12 radians per second. Okay, what does it mean that you have a natural frequency at 0? It will exhibit that mode, but it means that mode is a DC mode. So you're right. Your first frequency is the whole plane moving up and down. Does that make sense? Your first frequency is not a V. Definitely not. So your first frequency is the whole plane moving up and down. But wait, it's not what this shows. This shows kind of V-shape, right? But what is this? It's the direction, but what is V particular? Is this the mode shape? Yeah, it's got to be normalized, right, by that M inverse. But remember, the middle middle value of m is double the outside values of m. And so if you look at that, you'll see what's going to happen. So now we need to solve for our mode shapes. So u vector is equal to m negative 1/2 v vector, right? U is your mode shape. U is your mode shape. V is your eigenvector. So what's your first mode shape? So u1 vector 0.408, 0.408, 0.408. It's a nice mode, right? The mode goes up together. So it's like the space station, right? The first mode of the space station is just a displacement mode, which is one reason you have to mitigate vibrations. You don't want your thing just wandering off because of the vibrations. So anything, but typically the first mode of an airplane is also just a lateral up mode, right, or down. First mode of anything that's not fixed is going to be like that. So what's the first mode of a ship? Is the ship fixed? Yeah, I don't know either. I was all out the summer at the Navy, spent all last summer at the Navy, and that was like the joke. We're still trying to figure out what the first mode of our ships are. So I was like, really? They're like, yeah, it depends. It depends on in the design of a ship, it depends on the modeling assumptions you make. And they start those ships with just a beam, right? So those ship models are started by just a beam, and one of the ways that they study fatigue lives of ships is by giving that beam different stiffnesses and applying the wave loadings to it that are found in the ocean all the way around the world, and seeing, how stiff do you want a ship to survive your wave loadings? If you really wanted to design a ship for long life, you design it differently for the North Atlantic versus the Mediterranean, right? Different materials, different metals, different stiffnesses. Way off topic, but yeah. So I don't know what the first mode of a ship is. U2 is equal to negative 707, negative 0.707, 0, negative 7.07. So that's a good V mode, right? So the engines come up. And U3 is equal, what?
U2?
Yeah, it's fine. People got it. 0.66, negative 0.33, 0.66. Oh, no, wait. That is a typo. That is a typo. Your notes are correct if you're looking at your notes. The eigenvector for this one is not a negative number. That's a positive number on the bottom. Correct. So your second mode is actually your wings going like this. And your third mode is your V. And then this is, like Jude was saying, 0.707, right? Okay, so let's go ahead and take a look at our notes then. So if we plot these, oh, if you're bored now, it's about to get even more exciting. So just wait. Okay, so if we plot these, we get a first mode at 0 radians per second, which is just a DC offset, right? Your second mode at 1.72 radians per second are your wings tipping. And then your third mode is kind of the V shape, right? I honestly, like not having done this problem, I could have told you the first mode, because that's easy. I would not have known 2 and 3. Would have been two of those, right? I knew those would be the first two modes, but couldn't tell you which one happened first. And you could adjust those if you were really worried about what your modes are. You know, you could adjust the stiffnesses. Makes you think, does your second mode will have more energy than your third mode? Do you want a second mode like this, or do you want a second mode like this for controllability? Right? How do you want your wing surfaces to deform? I feel like if you have this, you might always end up turning to the left. Right? You just adjust your rudder, but I don't know. Thought process. Okay, any questions on that? What?
I mean, in the previous examples, we always kind of like thought about our mode shapes with respect to like the masses of the system. So like in the sense of a plane, if you're looking at mode 1 and mode 2 without considering like a ground reference, how can you tell that these are modes? It's just the thing tilting, but if you don't have a reference of what the horizon is, it's still looking like the same.
I don't know what you're.
Like the only thing that looks.
I mean, it's the displacement of your modes relative to each, right? It's
Right.
the displacement of this mode relative to these two modes. This mass relative to these two masses. Your center mass goes up, and all of your masses go up on the first mode. On the second mode, this mass goes down, that mass goes up. On the third mode, your two outside masses go up, and your middle mass stays the same.
But if like for mode 1, if all masses move with no displacement between the, like with respect to one another.
Yeah. So your whole plane kind of jumps up and down like a boat going through the water.
Okay.
That makes sense? Right? You kind of just float up and down.
Without like actual deformation of the frame of the plane.
Yes.
Okay.
But I mean, there's how that manifests itself in flight is a totally different discussion, right? And there's really not any information in a common fixed mode like that. I mean, once you start dealing with that stuff, it gets very specialized. So like this is something they considered a lot in the design of the space station.
If you were to excite that plane like a random frequency, would you see that first mode, or would you only see the second two modes?
I mean, if you excite it while you're flying, maybe. How do you excite something at 0 hertz? Push it. It's kind of a conceptual oddity. It's a good question. I don't have a good answer for you. I don't know. Can I answer that way?
They also said it was DC, so there's not technically a periodic signal, right?
I mean, that's the definition of a DC mode. Yeah, it's the definition of DC. So, you know, it's not something you're going to be able to like get to on the ground. Like you're not going to be able to test the plane to find your first mode. But it's there, and it is considered. And I know it was considered a lot in the design of the space station, right? So, but I don't fully understand why it was so dangerous for them. But for some reason it was. There's lots of cool papers from like the early 90s about structural control of space stations. And then it kind of fell out of favor. Maybe it's coming back. Okay, so that's a great way to do it. The mass normalized stiffness value, right? But let's go ahead and look at it with the generalized eigenvalue solution, or the general eigenvalue problem. Right, and so the general eigenvalue problem is k vector eigenvector. Actually, that might be a matrix. I'm going to leave it as a matrix for now. K vector is equal to vector the lambda m vector, right? I'm actually going to pull my notes off to the side so I can take a look. Oh, I have my M and my K mixed up. I always do that. No, I don't. All right. Sorry. Yeah. K vector lambda mv, right? Just haven't written the other way. So that's our generalized eigenvalue problem. So we can put this into Python or MATLAB or however you want to solve it, and we can solve for our generalized eigenvalues. This is going to give us lambda of 1 equals 0, lambda of 2 equals 3, and lambda of 3 equals 4.5. So that's the same that we got before. So our frequencies of our modes are the same, right? And then our eigenvectors are v1 vector is equal to negative 5.77. Sorry, I really suck at this. Negative 0.577, negative 0.577, negative 0.577. V2 vector is equal to 0.707, negative 0.707. V vector 3 is equal to 0.66, negative 0.33, and 0.66. Okay, so we can solve for our omega 1 equals 0, omega 2 is equal, what was it? 1.7? Is that right? Yeah. 1.7, and then what's omega 3? I don't have them. 2.12. Perfect. And those are all radians per second, right? All right. What about our mode shapes? U vector 1. What's our first mode shape? How do we get it? Yeah. We don't have to, right? Well, I shouldn't say that. So remember when we had this, we had U1 is equal to U1 alpha. What information is stored in our mode shape? The direction, right? So the alpha doesn't change the information, it just scales it. So in a way, you could say that our mode shape is our eigenvector. Oh, wait, maybe I had it V. It doesn't matter, right? If you set alpha to 1, you could use these eigenvectors. Does this eigenvector give you a uniform displacement for the first one? Does this one give you a tipped wing? And then does this one give you a V? Right? So you could use these for your eigenvectors. What might a benefit of scaling them be? Well, yeah, I mean, they're just the shapes. So I would see two benefits, right? One, in this sense, we could scale them to something that matches the previous one. So we just check if the numbers are the same. That'd be useful, right? Typically, and we haven't actually done it in this class at all, typically you just scale them to 1, right? So your max value is going to be 1. So if we look at this figure, right, this deflection would be at, this horizontal mode shape would be at 1. This would go from, 1 to probably, this will probably come down to like 0.45 or something. And this goes from -1 to 1 and 0. Typically, that's how you do it, just because there's no information in the mode shapes. Well, sorry, there's no information in the value of the mode shapes except that it's relative. So you could scale this, you could scale that. to get these the same as before, right? To get them the same as before, we had the two masses that we use to build our stiffness matrix. And one of the things that does is it normalizes it, right? That's why it's a mass normalized stiffness matrix. So we need to normalize these by a unit vector. So that means let's write it like this. So U of I vector is equal to, let's go VI over the norm of VI, and that's the three-dimensional norm of that vector, right? So then you could have alpha as 1 over the norm of VI if you wanted to write it like that. But it's all the same. And so if we do that, we get this plot. If we normalize it, we get this plot. And how is this plot different than the last plot? Should I like maybe put them right on top of each other or something?
Coordinates are changed. Just a different spot.
Yeah, so the okay, so the top one is done using the mass normalized stiffness approach. Right, so that's kind of K tilde, and this one is the general eigenvalue. Okay. So there's definitely a difference in the first mode, right? This first mode is negative, that first mode is in the positive. Generally a difference in the second mode, right? This one's down, that one's up, this plane turns to the left, that one turns to the right. Depends which way you look at it, I guess. But are they the same information? Information-wise, right? They're identical. Because there's no information in the mode shape other than the shape.